So up to this point, everything's been pretty straightforward, pretty simple with our projectiles because everything's been perfectly horizontal and we haven't had to deal with the fact that, well, most projectiles normally aren't perfectly horizontal when they get fired. They get fired at an angle like this pumpkin did in the pumpkin chunkin contest out in Iowa. So we're going to have to learn how to deal with angles in our projectiles, and that's what we're going to do for this next unit. So some of the key terms here to talk about. The first one is vector. So see our friend Vector from Despicable Me over there on the corner, this side you might recognize. Well, he does things with two things. He does things with both direction and magnitude. Okay. And a vector quantity is something that is measured with two components to it, direction and magnitude. Direction, pretty simple, which way. Magnitude is really how much. How much of something is there. Now, what would be measured as a vector? Well, it's something that's being measured as a velocity be measured as a vector because it has both direction and how much velocity there is. Acceleration can be measured as a vector, and displacement can be measured as a vector because all of these have both a quantity value and a directional component to them. So what we're going to be doing is looking at a velocity, and we are going to turn that velocity into two components. So if a component is a part of a vector that adds up to or subtracts from a vector. Okay. One of the key things to know is that we're going to describe vectors by an arrow. Okay, and that arrow has two parts to it. One is direction, and obviously that's by which way the vector is pointing. And two, the magnitude of it, the size of that vector, how much there is going to be indicated by the length. So the faster something's going, the longer the velocity vector is going to be. The more it's accelerating, the longer the vector length is going to be. Okay. So part of the vector that adds up to or subtracts from the total is going to be a component, and the resultant is going to be the sum of the components. Okay, and we'll get into what those components are going to look like with their velocity in just a second. So how do we do vector addition? How do we add two vectors together? Well, there's two different ways. One is called the head to tail method, and the other one is called the parallelogram rule. So head to tail method is pretty simple. If we have a vector A like this, and say we have a vector B like this, okay, and we want to add A plus B, we will take the end of A, the head of the vector there, and put the tail of vector B there, like so, and now this is our sum of A plus B. Pretty simple. Works pretty easily when things are on one axis, but also works when they're not on one axis. They're on different axes as well. The other option is to do what's called the parallelogram rule. So if we have two vectors, say we have vector A, and we want to add to that a vector B, like this, okay, we are going to take A and B, and we're going to make a parallelogram out of that. So we have A this way, and then we're going to take B and draw it from the end of A, and then we're going to take B, and also draw it where B was, and then we're going to draw A from here. Now we have a parallelogram out of A and B. And the end result of A plus B is this vector here from the starting point of each one to the point where they connect over here at the other end. So that vector there we could call vector C. So when we're doing vector addition, basically we are just adding these two things together to see what they're going to represent if we just had one vector that replaces both of them. And that'll be important to see when we get to velocities in just a second. So, but for a quick example, we have a boat accelerating from a breeze from behind it. So here's our boat, and there's a breeze from behind it at 1 meters per second. And that's generating an acceleration of 1 meter per second squared. And then the engine kicks in and generates a additional 3 meters per second squared worth of acceleration. What is the total acceleration? Well, the acceleration is just going to be the sum of those two vectors, or 4 meters per second squared. If we wanted to draw it, it would just be that 3 meters per second vector plus an additional 1 going on the end of it, or 4 meters per second squared. Okay. So that's how things work on the same axis. However, most of the time things aren't going to be on the same axis. So we're going to have to deal with multiple axes with our projectiles. So we're going to have to do some reversing of the addition to determine the components of the velocity. It's usually easy to measure the velocity of the object itself, but not the Vx and not the Vy. And that's our end goal is we want to find the combination of that Vx and Vy, and then we can use our free fall and constant motion equations to determine the path of the projectile, just like we've been doing when we've had a initial y velocity of 0. So how do we break a vector down into its components? Well, the idea here is that we're going to start with some velocity like this at some angle. Okay. And we want to know what is its Vx and Vy. Well, we can basically do the reverse parallelogram of this whole thing using the x and y axis. So we know the x-axis is here. We know the y-axis is going to be here. And this is where we pretend like it's the resultant. Where would the two components be? Well, they're really actually pretty simple to find. We're just going to go perpendicular to the x-axis and perpendicular to the y-axis. And where we intersect is where we're going to find a vertical part to our velocity and a horizontal part to our velocity. So whatever value this Vx has and whatever value this Vy has, if that object was traveling at that Vx and at that Vy, okay, so is doing both of those at the same time, what it would really be doing at is moving in the direction of the actual velocity of the object. We call that v prime in this case. Now you might be saying, okay, that's cool and all, but how do we actually figure out what those numbers are? Well, that's where we're going to use some trig functions. And trig functions just take advantage of the ratios between sides in the angle when we have a right triangle. And that's the key here. We're using right triangles. The reason we're going to use right triangles is because if this is a 90-degree angle, that's going to set whatever. If this is a 30-degree angle, this is always going to be a 60-degree angle, right? So what that does, it allows it to come with ratios of the sides to the hypotenuse based on whatever length it is. They're always going to be in the exact same ratio, because again, if I had a 30-degree angle there and I just made the bottom side longer, it would look like that. And the top side, the far side, so if the bottom side was longer down here, the far side would be longer by about the same ratio amount. Okay, these are similar triangles, and the hypotenuse would increase by about the same ratioed amount. Okay, so we're going to take advantage of that to generate these two functions that we're going to focus on. One is called sine of theta, and one is called cosine of theta. The sine of theta function is basically a whole list of values, all between 0, -1, and 1, that are in your calculator. You don't need to know what they all are. Basically, you're just going to use your calculator to do the math for you here. But it's the ratio, so sine theta is the ratio of the side opposite to your angle. So this is our angle here, and theta is going to define that angle. This is our opposite side here. It's the ratio of that opposite side to the hypotenuse, and that is sine of theta. Again, it's a list of numbers between -1 and 1 that's in your calculator that you don't need to know what they are. Your calculator knows what they all are. You just need to know when to press the button at the right time. Okay? But I also want you to understand that that's what that is. Okay? Cosine of theta is the other function we're going to use. And cosine of theta is going to be the ratio between the side adjacent to our angle, so that's this side here, and the hypotenuse. Again, cosine of theta, a set of ratios that's always going to be consistent based on whatever this angle is. Okay, the adjacent side and the hypotenuse side will always be in the same ratio. Again, this is all because we have this right triangle here. Okay. So we have these two functions, sine theta, cosine theta. There's a third one called tangent, but we're not going to need it for what we're doing. So we're just going to focus on these two. And how can we apply them? Here's how we're going to apply them for our projectiles. The two things we need are Vx and Vy. We need to know how fast horizontally the object is going, and we also need to know how fast vertically the object is going. And how are we going to do that? Well, we're going to take advantage of sine of theta and cosine of theta. Because if we have a triangle like this, okay, and if we have our velocity in this direction, there's our v. V is going to be our hypotenuse of the triangle. Vx is going to be, and again, this is going to be our angle from the ground. Vx is going to be that side that's right next to and adjacent to our angle. And Vy is going to be this side that is opposite our angle over here. Okay, so how can we find Vx and Vy? Well, sine of theta is the opposite side over the hypotenuse, or Vy divided by V. Okay, and if we move that around a little bit, it becomes pretty easy. It becomes Vy equals V sine theta. Okay, so all you need to do in your calculator is plug in your velocity. Say maybe it's 40 meters per second. And then we're going to multiply it by the sine of, say we launch it at 25 degrees. Okay, so if you put in the sine of 25 multiplied by 40, you're going to find out how much of that 40 meters per second is going vertically. On the horizontal axis, it becomes pretty simple as well. We're going to use the cosine of theta there, so we talked about. And there it's going to be Vx divided by V. So our Vx, which remains constant the whole time, is going to be equal to V times the cosine of theta. So again, if we did the same problem, we would have 40 meters per second times the cosine of 25 degrees. And that would tell you how much of the 40 meters per second is going horizontally. The other number is going to tell you how much that 40 meters per second is going vertically. Those two numbers are not going to add up to 40. That's not how it works. Okay, it's the combination of those two numbers together, vector-wise, okay, that's going to allow you to go up 40 meters per second at that 25 degrees. So give the worksheet a try. Try to find the Vx and Vy for each part. And then tomorrow you're going to have a video that you'll get on how we're going to apply that to determining the range, how far different projectiles go.